So hopefully everybody had a good break and we're kind of ready last couple of weeks here. Today we'll kind of finish up comparing populations and then we'll move into the next and final topic, which is linear regression. So after my class, I'm done teaching for today at, or this set of classes at 2, I'll put up a Learn Smart assignment. So that'll be the last and final kind of Learn Smart. So if you've missed any up to this point, make sure you do this last one to kind of help boost your grade up. If you've done them all up to this point, since I dropped the lowest one, if you miss it, ends up being your lowest one, it's a 0, right? But that's only if you've done and completed on time all the previous Learn Smart assignments, okay? So I'll get that up there. That'll be due before we start class on Wednesday, right? So it's a quick turnaround, just those short assignments, 10, 15 minutes. Kind of gets you familiarized with the last topic we're going to cover, which is linear regression, starting on Wednesday, okay? We also have the current Excel and Connect assignment. These are kind of the due dates, right? A little bit off still. But after today, we have covered pretty much everything you would need to complete these assignments. So I will tell you we'll have a 5th Excel assignment, and I'll probably put up a 6th Connect assignment and a 5th Excel assignment. So you'll have kind of one last assignment you can use to boost your grade. Now, if you've done the first 4 Excels and you've done the first 5 Connect homeworks, since I dropped the lowest one, if you're okay with your grade on those, right? You don't want to try to do better on that 5th and 6th one. You could not do those, get the 0, and that's the one that gets dropped, right? So if you front loaded your effort in this course, kind of these last couple of assignments, it won't feel like everything's as rushed, right? You kind of have a little bit more leeway, kind of given whatever the demands are from the other classes as well. So after today, I've covered all the material for these 2 assignments. After Wednesday, I'll then get up the kind of 6th Connect and the 5th Excel, right? And those will be there kind of as the very last assignments we'll have for those, okay? Any questions or anything before we kind of jump into material today? Was that clear what I was saying? I don't want you to just not do the assignments, because if you haven't done some already, those are 0s as well. So those, one of those will end up counting. But if you've done all of them up to this point, you're okay with your grade there. These after these 2, the next 2 I post won't be as crucial for you. Right? I also wanted to mention I put up an announcement about the problems where I had to give you the degrees of freedom. Right. So if you start working on that for those 2 problems, you don't have to use that crazy equation. I'm telling you what they are right here. The numbers, I think, for those ones should be locked in terms of the sample size. One other question has a problem, and I'll get an announcement up later. I was looking at it this morning. It's number 7, and it's dealing with proportions. And for some reason, it says to put it in proportions, which is what I intended it to be. But the algorithm is accepting the answer as percentages. So instead of 0.01 and 0.1, it would be something like 1% and 10%. So you have to put in that 1 and 10 instead of 0.01, 0.1. So I'll get an announcement up about that as well. So if you're having kind of issues on that one, that should take care of it there. Any other questions? We jump into it here. All right. So we've been kind of comparing 2 populations, whether or not that was 2 population means, whether or not that was 2 population, we want to know what the true difference is between the population means. So we have this difference in our sample means or this difference in our sample proportions, right? We can build confidence intervals, do hypothesis testing. So we're going to have one last measure that kind of compares 2 groups, but it's a little bit different. So we'll call it matched pairs, okay? So matched pairs is basically when you have the same individuals or the same subjects, the same companies, whatever the example is, but you have them at 2 periods of time. Or maybe you have, usually it's a before and after time period. You could do something like where you're comparing, the differences across groups within the same counties, right? Some type of demographic breakdown. More often than not, it's when you're looking at a before and after time period, okay? So kind of a setup example, easy toy example would be, maybe I'm a manager somewhere and they rearrange their workstations, right? Or they rearrange, how things are configured and whatever the office space is. And they want to know whether or not it improves or kind of detracts from or decreases productivity, okay? Well, you've got the same 10 workers and you've got a before and after time period. So really what we're thinking about here is that, maybe I see here's all my different employee IDs. I don't know, just making up numbers here. I think I'd have names. I just don't feel like making names up right now. So we have an after time period and a before time period, and we have their measured productivity. So maybe it's something like the units that they're creating or producing. And then before it was, I don't know, 6, 9, 10, 18. So what we're thinking about now is not finding the average productivity before and after, and then looking at the difference there. We're going to think about what is the average difference per worker. So for that, we need to find out how much productivity changed for each worker. So for this first person, it went from 6 to 10 units, 9 to 12 units. This person's productivity actually decreased, right? And we could find the change in productivity for every single worker, right? And that only works because we've got the same 10 workers before and after, right? We've got the same kind of subject pool, or the same sample, if you want to think about it like that. Once we have this difference variable, it really goes back to exactly what we were doing with one population. So if I think about, get this written down here, and I can speak. So if you think about when we had one population mean, we found the confidence interval doing something like this. Right? It's going to be exactly the same. It's just now we're going to use slightly different notation to identify that we found the mean of a difference variable that we created, right? So all this is going to indicate is that I'm still finding a sample mean, but it's of this difference variable that is using, right, two other variables right? We use two other variables to create it. But then it's the exact same thing. All we have is the variance that we can calculate from this difference variable. So we have a sample variance. So it basically is treated just like a one population example where we have a sample mean and a sample variance. The notation looks a little bit different, but it's just indicating that we're finding the sample mean of this difference variable we created. And our degrees of freedom now, I don't have to give you the assumed true degrees of freedom because it's not a nasty formula. It's simply n minus 1, okay? So it's really exactly like what we're doing with our one population sample mean, but only having a sample variance. The only added step is we had to create this difference variable, okay? Any questions on that? Okay, so, right, if I think about calculating this difference variable, right, from the before and after time period, we're using those two other variables to create that. Everything basically just goes back to one sample mean with only having a sample variance. It's just we have a little bit of added notation that identifies it's of this variable we created, which represents a difference, right, in two other variables. Okay. So if I want to do something like, you know, this manager productivity, maybe they go through all 10 workers, they find an average change in productivity of 8.5. They calculate the variance. If they wanted to build a 95% confidence interval here, right, how would they do that? Well, we've got this formula. The things that we need are the sample difference, the variance of that difference variable, and our sample size. Well, here we had a sample difference of 8.5, a variance of 121. I guess we have to kind of go back to remind ourselves, oh, where was it? Oh yeah, 10 workers, right? So our sample size is 10 here. Okay. So now I've got everything I need other than this t-value, the number of standard deviations away I need to go to build my lower and upper bound. Okay. So my degrees of freedom is n minus 1. So my sample size was 10. So 10 minus 1 is 9. I wanted a 95% confidence interval. So alpha should be what? Jumping back into this after break. 0.05, right? Remember, for a confidence interval, I've got a side on, or a tail, or you know, I've got two sides here. So I've got an area on each side of my confidence interval. So I divide alpha by 2. So 0.025 at degrees of freedom of 9. So we go to our t-table, right? Because we only have a sample variance. I wanted 0.025 on either side of my confidence interval at degrees of freedom of 9, 2.262. Now that I've got that t-value, I had everything that I need, right? Once I plug that in, to find my lower and upper bound. Right? So that was just plugging in the information we were given, looking up that t-value or the number of standard deviations away we needed to go to ensure that our confidence interval with 95% confidence includes that true average difference, or that true mean difference. Okay. So here, if we look at the lower and upper bound, what could I say about the change in productivity from this workstation layout? With 95%, what can I say about the average change in productivity per worker? Yeah, I've only got positive values, right? So that's telling me the true change, the true population difference in productivity is going to be a positive value, which implies that productivity has went up, right? We were taking the kind of after productivity minus before, kind of thinking about that change, okay? Any questions here on this one? I say it's not like it's anything completely new. When we do see how we do this in Excel, that might feel a little bit different than as we work through these. So we can also do hypothesis testing, right? So we can kind of imagine, if I look at what I was doing with the confidence intervals, with one population, this was how I calculated my test statistic. Make sure this is all showing up. There we go. Okay. So let's think about probably what is that test statistic going to look like for a sample difference kind of approach. Well, the statistic we're now interested in is the mean difference. We're going to have some kind of here, we don't end up using notation a lot, but you kind of think about, we have an assumed true population difference. And then I'm still dividing by, remember what this denominator represents is just the standard deviation, not of my sample means now, but of my sample difference, right? Over here, this was the standard deviation of my sample mean. So divide by the standard deviation of the statistic I'm interested in, which is just that variance we find, or yeah, the variance we find from that difference variable divided by my sample size. So it doesn't look a whole lot different. And just like with the other two population examples, more often than not in practice, we're thinking about an assumed true difference of 0, right? Can I reject the average change in productivity or whatever it is? Has it changed at all, right? Is that difference anything other than 0? Or is it greater than 0, less than 0, right? Did it improve or did it get it worse? So when it comes to the exam, right? Just like with the two population examples, I'm always going to be using assumed true differences here of 0, right? So it almost makes this a little bit easier. If I'm subtracting 0, I can kind of ignore what that assumed true value is. So let's take a look at a problem here. Whoops. So we've got the same 3 tests. The notation is a little different because we're just dealing with the mean of this difference variable instead now. But it's the same right, left, two-tailed tests, right? We find p-values, critical values the exact same way. Here's that test statistic equation. I said if this is, if I'm giving this to you as 0, this assumed true difference, this actually becomes a little bit easier. Right? So let's think about that manager example. Right? The manager had a sample difference of 8.5, variance of 121, and we said it was 10 workers, so a sample size of 10. How would I find the test statistic here? These test statistic equation or problems when it comes to the exam, hopefully as you're studying for it, as we get closer to it, it's really going to become probably hopefully the easier, this would be one of the easier problems on there because I'm given the information. I don't even have to calculate the sample difference from the data. I'm given it, right? If I go back here and this is on that formula sheet and I'm looking at it, I'm like, oh, I'm looking at the mean difference or change in productivity, right? So I've got that sample difference given to me of 8.5, variance of 121, 10 workers. If I'm thinking about kind of just testing for whether or not it's changed at all or whether or not it's improved, it doesn't matter, and whether I'm not thinking about it being greater than 0 or not equal to 0, that assumed true difference there will be 0. I'm just plugging in those values. Right? Now, this assumed true difference would come from a normal alternative hypothesis. So if I go back, I think the original question I had up here, if I can find it, has productivity improved? So maybe we've got the null and alternative hypothesis here being, if I'm thinking about has productivity improved, What I'm really saying is I want to test for whether or not that mean difference is greater than 0. Oops. So let me blow this up a little. There we go. Which means I'll assume the opposite is true, which is that it's less than or equal to 0. So I've got this sample difference. And if what I assume to be true is in fact true, it should be centered around this assumed true difference of 0. I found a sample difference of 8.5. So if I have a right-tailed test here, because I have a greater than sign of the alternative. So a right-tailed test, I found evidence on the right that goes against the null or supports the alternative. I could find my p-value by converting this into a test statistic or a t-statistic here coming from a student t-distribution, because all I end up having is a sample variance. So I'll turn this into a test statistic, which is the kind of step that we were on right there. We're just plugging in our values. So if we do that, oh, where is it? There we go. Just plugging in the information I was given, we get a test statistic of about 2.44. Okay. So when we're dealing with a student t-distribution, it gets a little bit tricky in that if we want to use the p-value approach, right, I want to find the probability that I saw the sample evidence that I did or anything further from that assumed true difference. I can look that area up on the table because I've got the t-value, right? I've got the test statistic now. Now the problem is with the student t-table, if I go to a degrees of freedom of 9, so I go down here to my degrees of freedom of, let me see if I can keep this all in here, 9, and I look across, I don't see 2.44 anywhere in this table. Right? However, I know that the area to the right of 1.83 is the area to the right of 2.26 is 0.025, and the area to the right of 2.8 is 0.01. So if my test statistic is somewhere in between these two t-values, then the area to the right will be somewhere in between 0.01 and 0.025. Is that clear as to why? So let me see if I can get this here. I think I can do. So it's 2.26 and 2.82. So what that table told me was 2.2 something, 8 maybe. The area to the right of 2.28 at that degrees of freedom was 0.025. And then the area to the right of that test statistic of like 2.8 was 0.01. So if my test statistic is somewhere in between there, then I know the area to the right has to be smaller than 0.025, but greater than 0.01. So I can't actually put an exact number to it using that table. All I can do is kind of put these bounds on it, say that it's in between these two values. Okay? So on the homework, this is kind of a fair game to be able to have to kind of put it in this range. On the exam, I'll tell you right now, like if you have to use a student t-distribution, I'll give you numbers that work out to be a test statistic. That's exactly one of the numbers that's in that table, right? So you wouldn't have to put it within a range. If this was on the exam, I would have given you something so that the test statistic worked out to be exactly, I don't know, 1.833, right? Or something that you could find on this table, okay? Any questions on that before we keep moving? Now, what I also could have done here was use the critical value approach, right? I could have said, okay, well, if I've got this degrees of freedom of 9, what would the cutoff values be that give me these different alpha values in the tail, right? So here, if I use my kind of traditional alphas, right, 0.1, 0.05, and 0.01, 1 point, and I'll blow this up in a second, just writing these down so I don't forget them. So 1.383, right, is the critical value that gives me 0.01 in that right tail. Then here's kind of my rejection region. And then 1.833 is the critical value that corresponds to having 0.05 to the right of it. And then 2.821 is the critical value that corresponds to having 0.01 to the right of it. So I can use my critical values and then plot my test statistic against it. So here my test statistic was what, 2.4 or something like that. So that would be right about here, which is in the rejection region. Actually, I think I said 0.1 and I wrote down 0.01, right? That should have been 0.1. So it's in the rejection region at the 10% level. So I can reject with 10% significance or 90% confidence. It's in the rejection region at the 5% level. So I can reject with 5% significance or 95% confidence, but I can't quite reject at that 1% level because I'm not quite in the rejection region there. So I can use either approaches there and come up with the same rejection decisions. Remember, if I had taken that p-value, which I said I could only kind of put a range on that. Well, if my p-value is somewhere in this range, then my p-value will, if it's less than 0.025, it's definitely going to be less than 0.1 and 0.05. So I'd reject. But if it's greater than 0.01, well, then my p-value wouldn't be greater than alpha, so I'd fail to reject. So I'd make the same rejection decisions. I think it's just when you have to put a bounds on the p-value, I think the visual with the critical value approach makes a little bit more sense. Or it's easier to see. Any questions on anything here? All right. So let's see. I hopefully have. I didn't even have all that kind of in the slide, so it's kind of a good thing to be able to kind of work through those. Make sure we know how to find critical values, etc. So I think what I'll do is, where are we at in time? I'll present this next one, and then maybe I'll have you guys work a little bit on some hypothesis testing stuff. So we already have worked through a confidence interval problem. I'm just going to give another type of example we can see for this match difference. So maybe it's something like, I don't know how long ago this was now, but I remember when they started, they used to not like post calories right next to the food when you go to fast food places or whatever. And then I think there might have been a law or something, but then you started seeing them pop up everywhere, right? So maybe a relevant question would be, did people change their calorie consumption after they started posting this, right? So maybe you've got, some customers that you can track their purchases because they have some type of card. So I think about here, like a Starbucks card. So you've got the same 40 people and you can observe the items they purchased before and after the calories were posted and see, did the average calorie consumption per person change after they posted them on the menu? Okay. So you find a sample difference across these 40 people of 2.1. You got a variance of 64. What if you wanted to calculate a 99% confidence interval for what that true difference is? Okay. Well, if we look here, it doesn't look like we can rule anything out because 2.1 appears at least to be pretty close to the, without doing all of the math, looks like it's in the middle kind of all these confidence intervals. But really, this just goes back to, we've got this equation, right, for our confidence interval. We have the sample difference, we've got the variance of that difference variable, and we have our sample size. The only thing left to do will be looking up that t-value. Right? So here, with a 99% confidence interval, our alpha would be 0.01. We would divide that by 2, right? Because we've got an area on either side of our confidence interval. So 0.005 would be the area that we want on each tail. Right? So that's the t-value we want to find. The t-value gives us 0.005 in each tail. Our degrees of freedom would be what here? Just the sample size minus 1, so 39. So we would go, well, I jumped the gun there so we can see it, but, right, 0.005 was the area I want in the tail. I got to scroll all the way down here to a degrees of freedom of 39, 2.708. Right? Well, now that I have that, I've got everything I need to kind of plug in all my values and find my lower and upper bound. Okay. So with 99% confidence, what could I say here about the change in calorie consumption? So we found it now. Then I already forgot the values. No, I don't want this. Negative 1.3 and 5.53. So maybe these are a little off, but. So here's my upper and lower bound. Remember, this is telling me where that true difference is, or that true change in calorie consumption per person is. Well, with 99% confidence, it could be a positive value, which would mean calorie consumption went up. It could be a negative value, which would mean calorie consumption went down per person, or it could even be 0. Right? So here at the 99% level, I can't really say anything, right? Because that true difference could show that calorie consumption went up, down, or didn't change at all. Right? So sometimes, we build these confidence intervals, we can't say anything with that level of confidence. Now, as we want to say things with lower and lower levels of confidence, what happens? Well, lower levels of confidence actually correspond to higher alphas, right? You kind of think about going from the 99 to the 90% confidence. Alpha gets larger. That means you don't want you kind of want more area or higher probability in your tail. So it pushes back that t-value. Well, if it pushes back the t-value, right, this gets smaller. I have a smaller margin of error. My confidence interval is going to get narrower and narrower. So that maybe with 90% confidence, I could say that the change is positive. Right? I don't know. I'd have to work through the numbers here. But at least, saying things with a lower level of confidence, that would decrease that kind of width of my confidence interval. And maybe at like the 90% confidence level here, I could say that the calorie consumption went up. Because my sample evidence, right, what my confidence interval was built around was that sample difference. Remember, we found that was positive. It was 2.1. Oops. All right. So if I started saying things with lower levels of confidence, maybe I could get kind of range of values where that true difference is actually only positive values. But, saying something with 80% confidence isn't as good as saying it with 99. So even though we might be able to say it is only positive, we're doing it at a much lower level. Any questions there before we keep moving? So I forget what meme. Oh, the barista asked for my name, I guess you think. So if you guys haven't seen Napoleon Dynamite, I don't know if I've used a meme from this movie yet in this class. It's getting pretty dated at this point, but you should definitely go watch it. It is very dumb, but very funny. So, and I have an impression of Kit, but I don't do it in class. So what if we wanted to do some hypothesis testing with the same example? Okay. So I've got the same 40 people, and I want to know, has calorie consumption decreased? So if I'm thinking about what I want to test for is whether or not calorie consumption has decreased, what would my alternative hypothesis be? Is that true population mean difference, calorie consumption decreased, and that difference would have to be less than or greater than 0. See some people pointing down. Right? So the difference, I'm assuming that means you're thinking if it's decreased, what you're trying to test for is whether or not that mean difference is less than 0, right? That would mean that calorie consumption has gone down. The after time period would be smaller than the before. So that's what we want to test for. We assume the opposite is true for our null, which is greater than or equal to 0. So I look at my alternative hypothesis, I have a less than sign, so I have a left-tailed test. So here my critical value should be what? Can I say anything about my critical values for a left-tailed test? Yeah, they will always be negative, right? Because I'm looking at the left side of that distribution, right? And I know that the student t and the standard normal, which we're not using right here, but both of them are centered at 0. Right? So the left side will have negative critical values, right side positive. Okay? So hopefully we'll follow along here. The little points that I want you guys kind of just try to work through these, because like I said, I hope these test statistic ones are ones where you guys can kind of get easier points in the exam. If we get comfortable, we're really just identifying information from the problem and then using that formula we have to find that test statistic. So we go back, remember what we were doing before, right? Here was my equation for that test statistic. I take my sample difference, subtract the assumed true difference, and then divide by the square root of my variance over my sample size. So here we had 40 card holders. Remember the null and alternative hypothesis. We had a left-tailed test when we were saying, is it less than 0? So we've got our assumed true difference here from our null and alternative. You had 40 individuals, right? And this was the sample difference and the variance that you found. So give you a little bit of time to kind of work and come up with that test statistic. Once again, remember the sample size we had here, we had 40 card holders. Okay. All right, go for another 20 seconds here. 20, 30 seconds. All right. Then we got an answer and take your best guess here. We got 26 of us here today. And close it out. All right. So first of all, which of these can I rule out right away? Yeah. So the difference we found, right, was actually positive, right? So this is going to be one. It's a little bit tricky, right? So the value of our, well, it shouldn't be tricky in the sense of the test statistic, but if we kind of continue with this example, it'd be tricky. So if I find a sample difference of 2.1, remember what my test statistic is telling me is how many standard deviations away I was from that assumed true value, right? So if I think about the distribution of my sample differences, that assumed true difference should be what? All right, we assume, so we had less than 0, so that kind of cutoff value that we're testing, that we're assuming that it's equal to, is at 0. Right? We found sample evidence that was above that. So when I'm coming up with my test statistic is telling me how many standard deviations away I am from that assumed true difference, which here, I'm going to be a certain number of standard deviations above. So my test statistic should actually be positive. Right? The only way I would have a negative test statistic is if I found like a sample difference that was actually negative. Okay. But the reason why I understand the confusion is because this is a weird one where if I think about my original null and alternative hypothesis, actually, I'll just write the alternative here. Well, I'll write both. So we had less than 0 and then greater than or equal. I actually found sample evidence that supported the null. So without doing p-values or critical values, right away I know, can I reject or fail to reject the null? Well, if I find evidence that's consistent with it, why would I ever reject it, right? So this is one where if we looked up p-values, it'd be kind of weird because we have a left-tailed test. So the p-value would be area to the left, it would be massive, right? So we would fail to reject at all levels. And if we kind of work through this, it wouldn't make a whole lot of sense because right away we know we found evidence that supports the null. I don't even have to go through the rest of this process. So you're right, this one probably would be better. Maybe I shouldn't have went in with these assumptions, and maybe I just want to see, well, has it changed at all, right? And create a two-tailed test, then evidence on either side would kind of go against my null. But I didn't, right? The way this was constructed, we had this as a left-tailed test. Oh, sorry, that was off the screen, right? So we had a left-tailed test. So we worked through the rest of this, wouldn't make quite as much sense. But it would be very similar to what we did before, right? We could find the critical values, think about the rejection region. for a left tail test, those are all going to be negative. So just to kind of walk through that real quick, if I looked up, I had 40 workers. So 39 was 9 degrees of freedom. So the area that I would want in the tail would be 0.1, 0.05, and 0.01 to find my 3 critical values. 1.304, 1.685, 2.426. So those would be my 3 critical values. So that one at every single level. But those values, then what else would I need to do to them for a left tail test? It's those same 3 values, but negative, right? So the student T table kind of has a picture up here. Is always looking at the right tail. We were looking at the left tail. It's symmetric, so those same 3 values, but negative. Okay. Any questions on that before we keep moving here? All right, so I have this file up on Canvas, which I think my original example at the beginning of the semester was kind of looking at county suicides. But then I thought maybe something a little more relevant, at least given the climate we're in, is doing something with some COVID data. So I got I come out, goes in waves where I become interested and uninterested in the data that is revolved around COVID. But for whatever reason, last week I was. So I have this file, and I've got different, I think I've got deaths, I've got cases, and then I've got kind of the death percent, right? So the percent of people who die once they contract the disease. Okay? So one thing I think is a little interesting is to take a look at this. So let's go, this one I got to blow up too. So the original data I have here in this cases class worksheet is these are counties. So every observation represents a county. Okay? Here's their IDs. I don't have the names in this file, but you can get them if you really want to. I had kind of the number of new cases that they saw in 2021 and 2020. I then also divided those by the population to account for the fact that, if I'm looking at, I don't even know what county to pick on, but like maybe J County is pretty small, right, in terms of population. They're definitely going to have far fewer cases than, I don't know, I don't even know the county names around Indy, but pick a county around Indy, right? They're going to have way more cases because they have more people. So we kind of divide by the population here to factor that out, right? So what we could then do is think about, maybe I want to do a right tail test, right? And I want to say, have the number of cases from last October, right, 2020 to this past one in 2021, has that average change in the number of cases went up or down? My initial instinct would be that it probably goes down because within that time period, you have vaccines, right? And so, we could start out with a right tail test. We think, let's test for whether or not the number of new cases has gone up, right, on average. So I create this difference variable, right? And now I'll delete this and kind of show you how easy this would be to do kind of on our own, where I'm going to say, okay, take 2021 cases and subtract the 2020 cases per person, essentially. I kind of factored in the population. Hit enter. So I've done that for the first observation. If I go over here, and this becomes like this thick, plus sign, if I double left click, it'll fill that in all the way down to the very last observation. And the way that I just shot down to the bottom real quick, I'm just using Control Shift in the down arrow, just like you would when you're filling in a formula. Makes it a little bit easier to navigate instead of scrolling, especially if you're on a laptop. Okay. So I now have this difference variable. What I'm going to do, and honestly, I don't even know, I forget what the results are for here. So I can find the mean of this difference variable, right? That's just using the average function. So I Control Shift or Command Shift on a Mac, hit the down arrow, hit enter, pops me back up at the top. I can find that sample variance of that difference variable. Once again, Control Shift, Command Shift on a Mac, hit enter. Notice the variance is pretty small here because I'm dealing with very small numbers, and then I can find my sample size. I believe it's almost all the counties. So this is a pretty big sample size, right? So I'll use that count function to find my sample size, or N. So here I can have Excel be a calculator for me, right? I can say, all right, take that sample difference that I found, right? Or that sample mean that I found. So if let me see if I can throw something up here, I'll be a little bit small, but you can see as we're working through this, all I'm using Excel to do is be a calculator to find me this value. I've got the assumed true difference of 0. Divide that by the square root of my sample variance divided by my sample size. That's as simple as that test statistic equation is, right? So I'm just using Excel to be my calculator here. Okay. Any questions on anything up to this point? This shouldn't look a whole lot different than things we've done. I want to find the p-value. So I have this ridiculous test statistic, by the way, 46.5, right? So if I want to find my p-value for a right tail test, it's the area to the right of 46.5. Well, if I use t-dist, right, and I click on this, comma, my degrees of freedom is my sample size -1, and then comma 1, telling it make it cumulative, like give me the entire area to the left. Well, that's close to my p-value, but I have to do one more thing, which is what for a right tail test? My test statistic was 46. I want the area to the right. Yeah, this tells me the area to the left. So I heard someone come mumble. I have to subtract that from 1 still. Right? So I basically have a p-value of 0 here. I mean, I saw something 46 standard deviations away from the mean. But the crazier thing is, if I set up as a right tail test, this is actually telling me that with any level of confidence I want, the 99.9999%, I could actually say that in the last year, on average, what has happened in the number of COVID cases per person across these counties. So if I have a right tail test, right, I want to test for whether or not it was greater than 0. So the assumed true value was that it was less than or equal to. So the p-value like this small, I could actually reject that null. I could reject that the difference is negative, which is kind of wild. Right? I'm saying that I can reject that COVID cases went down in the last year, which was very counterintuitive to me. Now, obviously, this is not an end-all be-all. We'll actually, with regression, we'll probably revisit this and see how things will change if we can account for other factors. But what's interesting is that with a high level of significance, I can say that the number of cases in the last year have actually went up on average, across these counties. Now, I could do the same thing with deaths. We could do that pretty quick. But I want to do this death percentage one since we only have about 8 minutes left. I'll kind of show you one more example. Where I want view. There we go. And it's going to be pretty similar. I'm just going to go through it pretty quick. A couple little differences that I want to show you. So I'll do this real fast, right? I'm finding the mean. So I'm going to use that average function. Now here, I have the death percent, kind of so the percent of people that died, that contracted the disease. Same thing, comparing 2020 October to 2021 October. I kind of have a 1 year difference, comparing the same month. So I'm not comparing July where it's warmer and people are outside and not inside more. So I'll take the average of that difference variable. It gives me my kind of mean difference. Sample variance using that var.s, and then my sample size. Okay. Same 3 things I had before. I'm going to use Excel to be my calculator. So here's my average difference. Now here, I'm going to put my assumed true difference up here because I want to show you something. Okay? So I'll put a 0 in there eventually. And then I'll divide by the square root of my variance over my sample size. So it's exactly what we had before. Right? It gives me my test statistic. Now so I'll put my 0 in up there. Shouldn't change anything, right? But I want to use it to make a point in a second. So here I've got a much smaller test statistic. So if I wanted to find my p-value, let's say I have this as a 2-tailed test, there's actually kind of something that's kind of convenient. And I think I showed this to you with in the last, the video kind of I taped from last Monday. So if we do t.dist.2t, right, I can tell it my test statistic, comma, tell it my degrees of freedom, and it will automatically find the area that in whatever tail it is, depending on if the test statistic is positive or negative, and then multiply it by 2, right? Because if it's a 2-tailed test, I can find the area in the tail, and I have to multiply it by 2, because I know it's equally as likely for me to see something that went against the null on the other side, right? So that's kind of nice and convenient. I get my p-value there. It's huge, right? So here, we think about what my null alternative were. So what I want to test for was whether or not this difference is, let me see. I'll put a symbol here. So this is going to mean not equal to 0 for right now until I can change this to get an, let me put a want a symbol. Not equal to. There we go. Copy this. Why won't it let me copy and paste this here? Oh, maybe because I'm holding the wrong key. All right. So that's my alternative, which means my null is that it's equal to 0. Right. So the p-value of 0.5, is that going to be less than any of my alphas? It's not less than 0.1, 0.05, or 0.01. So I fail to reject the null at all levels. So, oh, and this should not be a p. Sorry, this was supposed to kind of represent a 0. Right? So with all levels of confidence, I fail to reject the null, which the null was that difference is 0, that it hasn't changed at all. So despite having the vaccine kind of in 2021 in October as opposed to 2020, it doesn't appear as though the death rate has changed at all, right? And maybe there's a million reasons for this, right? Like I said, hopefully with regression, we can dive a little bit more into this and kind of figure out, we can control for some of these other factors that might be correlated with some reasons why this difference has gone up. Right? Any questions on anything? I got one more thing I want to show you before we get out of here today. So I just same setup, right? That's a very rudimentary kind of look, but you'll see these used a lot. Like in some of your upper level courses, I think you'll probably start getting into these issues where you use, especially I know one of the high level marketing uses this a lot, but you use a lot. They call them t-tests, right? You're just looking for differences in two populations or differences in the same population, but two periods of time. So one nice shortcut that we can use is this t.test function. Okay? So the way you use this is you select your first variable. So we had 2021, comma. This one's a pain because I have to scroll up and down if I want to show it to you. The second variable I had was 2021 death percentage. All right. Scroll back up. Then, comma, I tell it the number of tails. Well, I had a two-tailed test. And then, comma, the type of example I have is a matched pair. So I would put a type 1 in here. The other one that we used on that video Monday I went over was when we were looking at the difference in sample means, that was where you can use that t.test, but you put a 3. Here, we're not comparing two sample means. We're finding just the mean of this difference variable, right? So I'll put a type 1. I have matched pairs, and it should give me exactly the same thing as if I broke this down to steps. Now, the issue with this is I can't see my test statistic, right? The other issue is this always tests against an assumed true difference of 0. So let's say instead, I want to say, can I just say that, maybe can I say that this is greater than, I don't know, negative 0.01, right? Just to have an example. Well, that will change my test statistic, which will change my p-value here. But notice for that t.test shortcut, it doesn't update at all because the only value that it can accept is an assumed true difference of 0. So it comes in handy for like this class, but outside of this class, when you're moving forward in practice, that t.test is going to have its limitations, right? And that's where knowing how to do this by breaking down the steps, you actually have a lot more power. You can test against a lot of other values, not just 0. Any questions you want to see CSL again before we kind of wrap things up for today? So I'll put up that last final Learn Smart that'll be due before we start class on Wednesday. They'll kind of introduce the idea of linear regression. We'll start diving into that. And that's really the last and final topic. We'll just probably be doing a lot of examples of that.
What days are final?
I can't remember off the top of my head. We can look it up here. I'll end this, but then I'll look it up. So, yep. All right. I'll see you guys on Wednesday.